Hello everyone, welcome to the second lecture of this course Hydraulic Structures. Here we'll discuss about gravity dam and forces and its stability analysis. So a gravity dam is based on the principle that a heavy object is difficult to move. That means most of the resistance that it gains against the external forces is due to its own weight. So it is mostly made of concrete or masonry, and the typical shape of a gravity dam is like a right angle triangle, and the basic right angle triangular profile is also called the elementary profile of the dam. So in this case, this dam, if we only consider this kind of a section, which is a right angle triangle, then that part is called the elementary profile of the dam. And this portion, this point, this bottom corner, bottom upstream corner is called the heel of the dam, and this corner, the downstream corner, is called the toe of the dam. So it's basically like our feet, where this is heel and this is toe. Then some width is provided at the top, which is this portion, so that some vehicles can at least move on top of the dam for transportation and other purposes and maintenance. And sometimes, to give it some additional stability, the upstream face is also made slightly inclined or provided with an extended heel. So sometimes the gravity dam may have a slight inclination towards the upstream surface, on the upstream surface as well, like this. And sometimes, instead of sloping the entire upstream surface, only near the bottom we provide some extension of the heel. So it gives some more stability to the dam. Then, so let's discuss the forces that will be acting on a gravity dam. So the first force is the hydrostatic force, that is force due to water, and that will be, if this is the dam, then on the upstream side we'll have the water in the reservoir, and this water will be exerting the hydrostatic pressure, which will be 0 at the top and maximum at the bottom, and in between it will vary linearly. And this amount, the hydrostatic pressure at the bottom, is equal to H rho g, where H is the total depth of water present in the upstream, which is measured from the bottom of the dam. Then comes the self weight of the dam, which is, you can find out simply by calculating this area and then multiplying it with the length of the dam. And for simple calculations, instead of the total length, we only take unit length. So weight per unit length of the dam we can calculate just by calculating this volume and multiplying it with gamma, or specific weight of the material, which is concrete or masonry. Then friction is another force, which is actually not an external force exerted by anything. It is a resisting force against movement, which is, if this force is acting in this direction because of the hydrostatic force, then the surface, that is the river bed, will be exerting some friction on the bottom of the dam, and that frictional force provides the dam the stability against sliding. That means the sliding movement in this direction. Then comes another force which is called the uplift pressure. So that is the pressure exerted by water stored in the pores of the foundation soil. So if we ignore these things, so the soil or the foundation soil, that is whatever material is the river bed made of, it will have some pores because it is basically soil, and so through these pores water will seep in. So these pores will also be filled with water, and these pores will this water filled in the pores will also exert some pressure, and the direction of that pressure will be obviously normal to the bottom surface of the dam, and that normal direction is the upward direction. So this upward force is called the uplift pressure. We'll discuss this later in the lecture. Then comes another force which is due to the silt pressure, or the pressure due to the sediments, and that will be because of the sediments deposited at the bottom of the reservoir. So here with time some deposition will take place because all the sediments that are carried by the river will be deposited near the dam because it has very low velocity at that point, and this silt or sediment may exert some additional pressure at the bottom of the dam. So that is the force because of silt pressure. Now in addition to these forces, there are some other forces as well. So they are the earthquake forces, which will be generally considered in earthquake prone zones, then wind force due to wind, then force from waves, then force due to debris which will be carried by the river, which may strike the dam surface, and so for those forces are also to be accounted for, and force due to ice. So the force due to ice may also be because of impact of ice sheets on the dam surface, which will be floating on the water surface, or sometimes if the entire water surface gets frozen, then we know that water expands when it freezes. So that expansion of this water surface may cause some additional forces on the dam. So these things are this ice pressure is relevant in cold conditions, cold regions, and in some places it may be ignored. For our course, for this course, we'll be mainly focusing on the first four forces, that is hydrostatic force, then self-weight, friction, and the uplift pressure. So let's first discuss about the hydrostatic force. So hydrostatic force may be from two directions, that is one from the headwater, that is the water stored in the upstream, and the opposite direction, there is tailwater. That means the depth of flow available in the river downstream of the dam. So this will also exert some pressure, although it will be smaller than the head water pressure. And to calculate this force due to hydrostatic pressure, it's quite simple actually. So to calculate head water, force due to head water, we only need to know the height or depth of water in the upstream in the reservoir. Then let's say it is capital H, and in the downstream, let's call it small h. So the pressure from the upstream, let's call it pH, pressure from headwater. Because we are talking about force, let's give it the name FH, will be equal to pressure multiplied by area. Now the pressure in this case is variable, it is not a constant pressure. So we may take the average of this pressure between 0 and this value, which will be H rho G. So that will give us half of 0 and this average between 0 and H rho G. Then the area will be equal to H multiplied by 1. This 1 is because we are considering unit length of the dam. Unit length means, as I've mentioned before, if you consider this 1 meter or 1 unit length of the dam, then it is unit length, and on that unit length of the dam we are going to calculate this hydrostatic pressure force. So that will give us half rho G into H squared. So that will be the force because of the upstream or the headwater, and this force is in the horizontal direction. If we provide an inclined surface of the dam in the upstream, as I mentioned before, in that case the hydrostatic pressure will be on this portion. If there is any vertical surface underwater, then the calculation will be simple. It will be like this, the pressure distribution, but on this inclined portion the pressure will be acting normal to that, and therefore its direction will be inclined. But to avoid that confusion, avoid that complication, what we'll do is we'll simply divide this inclined force into its horizontal and vertical components. So the horizontal component is simply equal to whatever we have calculated before, and the vertical component of hydrostatic pressure force will be equal to the weight of liquid directly above the surface, the inclined surface. That means in our case this much is our inclined surface in this figure. Then we'll have to calculate the weight of this portion of water, or this wedge shaped volume of water. So calculating the volume of this wedge shaped water is not a difficult task. So let's call it FV. Then it will be weight of water above the inclined surface, inclined face of the dam. So this is how we calculate the forces due to water on the upstream surface. In the downstream surface also it is similar. The only thing is that in this case the force will be, let's call it F small h, will be half rho g into small h squared, which is the horizontal force on this surface, and the vertical force on this surface will be equal to the weight of, let's call it F small v, equal to similarly the weight of the water directly above that inclined surface. That means weight of this much volume of water. Again, the calculation of this volume is not very difficult, it's simple geometry. In this case also there is no difference, so it's the same thing. Next comes self-weight. Self-weight is actually very simple to calculate, but for calculation purposes, what we generally do is, if we have a dam with a shape like this, then what we generally do is we divide this into even simpler shapes. That is, this is a triangle, then from here to here this is a rectangle, and the remaining part is again a simple triangle. So you can, for calculation purposes, you can call this one, suppose W1, weight of this portion as W2, and weight of this portion as W3. Although calculating the total weight is not that difficult, but we are dividing it into 3 parts because further later on we'll see that it's not just the weight, we'll also have to find out where the weight is acting. That means the center of gravity of this entire dam. So for this kind of a for this structure, for this shape, finding out the center of gravity is not that simple. So what we'll do is we'll divide it into these 3 parts, and then finding out the center of gravity is much easier because here it will be 2/3 of this distance from here. Then for the rectangular part it is right at the middle, and again for this part it is 2/3 of this distance from this corner. That means somewhere around here. So these are the points to which these weights will be acting. So these are the center of gravities of these sections. Again, to calculate the actual weight, we simply have to find out this area, then multiply it with the unit length, and then multiply it with the gamma or specific weight of concrete or masonry. So this is how we calculate the self weight. Then comes uplift pressure. So as I've mentioned in the introduction, the uplift pressure is the pressure exerted on the bottom of the dam by the water stored in the pores of the foundation soil. So if this is the foundation soil which has pores, then those pores will be filled with water, and that water will be exerting some pressure in the upward direction. Now what will be the magnitude of this pressure? That we'll see. At the heel of the dam, the uplift pressure is equal to the headwater pressure. That means right at this point, if you consider, then obviously whatever is the pressure in this direction, that is because of this entire column of water, this entire height of water. So the same amount of pressure will be acting in the upward direction as well. Let's use a different color to have contrast. So in this direction, whatever is the pressure will be equal to capital H rho G at this point, that means at the heel. Now, if you take this point, at this particular point, the pressure is equal to whatever pressure would be exerted by this height of water, which is small h rho G. So, therefore, at this point, in the upward direction also, the pressure will be small h rho G. So, we have found out what will be the pressures at the heel as well as at the toe. Now, in between, how the pressure will vary, there are lots of research going on to find out the exact variation of this pressure, but for all practical purposes, it is recommended that we assume the pressure to be varying linearly. That means a constant pressure drop per unit length in this direction. If we talk in terms of the dam, then this direction is actually its width, or we can say that per unit width of the dam, same amount of pressure is being dropped. If you consider this point, then you can simply calculate what will be the pressure at this point, assuming this kind of a linear variation, and that way we have this kind of a pressure distribution acting at the bottom of the dam. As you can guess, this kind of pressure, this uplift pressure, is not favorable for a dam, and it decreases the stability of the dam because it's trying to lift the dam and therefore eliminating or cancelling out some of the weight, some of the self weight of the dam. The dam had a certain weight, but because it is already lifted by some amount of water, so the effective weight of the dam will be reduced by that much amount. So these are the ways to calculate the uplift pressure. Then comes the force due to uplift pressure. So to calculate the actual force because of uplift pressure, what we'll have to do is simply, again, just like in the previous case, the pressure at the two extremes, that means at the heel and at the toe, are given as h rho G and small h rho G. So if you take the average of these two, that will be the average pressure. So here the pressure is this much, here the pressure is this much. For the overall calculation of pressure force, we'll take the average of these two, which will be this amount of pressure, and which will be equal to half of the sum of these two pressures. So this is the average pressure. Then we'll have to multiply it with the area, and in this case the area will be this width of the dam, then multiplied by the unit length of the dam. That means this length, which is unity. So it will be B multiplied by 1. So this will be the uplift pressure force. Let's call it Fu. While doing some calculations, we'll also need to know where this force is acting. That means in reality the force is distributed all over the surface, but To do the calculations, we'll need to find out the resultant of this force, which will be somewhere around here, so that we can treat this force as a point force acting at a point rather than a thrust acting over an area. So in that case, we'll have to find out this resultant and its location. So for that, we'll have to again divide this uplift pressure diagram into two simple parts, one rectangular and the other one triangular. It is similar to what we have done with the self weight, because in the self weight we have divided this complex shape into three different simple shapes. Similarly, this upward force also we can divide it into this horizontal portion, this rectangular portion and this triangular portion, and from that we'll be finding out that this triangular distribution of pressure will be acting at a distance which will be 2/3 of the total base width from the toe, 2/3 of B, and the rectangular portion will be acting right at the middle, that means half of B. So let's call it FU triangular and FU rectangular, suppose. You can give any other names. So it is acting at 2/3 of B from the toe, and FU rectangular part, RECTRI, and this will be acting at B by 2 from the toe, or the heel is the same thing if it is at the middle. So this is how we find out the uplift pressure force and its location. So if you want, you can also find out where the actual resultant is. It will be somewhere in between these two, and if you want, you can use it by applying your knowledge of moments and resultants, but you don't have to do that. You can treat these two forces as separate forces and incorporate them in the numerical problems as you wish. Then the next force is the frictional force, and this frictional force is actually a resistance. So the force due to water will be acting in this direction, then if tail water is present, then it will be acting in this direction, and the uplift pressure will be acting in upward direction and the weight will be acting in the downward direction. So if sliding occurs, it will be in this direction, and therefore the resistance to sliding must be in the opposite direction along the interface of the dam and the river bed. So this is the direction of, let's call it FF, or the frictional force or the frictional resistance. So the frictional resistance will be calculated as some coefficient of friction multiplied by the normal force acting at this interface, that means at the interface between the dam and the river bed. This is because we know that the frictional resistance or the frictional force will be equal to some coefficient of friction and the normal force acting on the surface along the interface. So this normal force, find out this normal force, we'll have to see what are the forces in the vertical direction, because this surface, this interface is horizontal. That means normal to the horizontal will be the vertical forces. So we'll ignore all the horizontal forces and we'll only consider the vertical forces. So in this case, the vertical forces will be the weight of the dam and the uplift pressure. So frictional force will be equal to the weight of the dam, W, minus the uplift pressure. But in this particular example, we have this inclined surface of the dam in the upstream, and if tailwater is present, then we also have this portion of the inclined surface underwater. So this volume of water and this volume of water will also be acting in vertically downward direction. So these two forces will also have to be considered here, and that will be those two forces will be added to the weight because they are downwards. So we'll add, let's call it F capital V plus F small v. So these are the forces in the vertical direction, 1, 2, 3 vertical forces in downward direction and 1 vertical force in upward direction, that is the uplift pressure. So this is how we find out the frictional resistance against sliding.